we call a theory whose interaction of the form public constant of the real fields, the real scalar phi. From here, we were interested in the following decay process. These moves the quanta of this real scalar phi, we were the following decay process. Let us say that we are looking in this decay process, and what we were interested was calculating because this is one. We are calculating this thing, and this cannot be the following. Z is got to be equal to 1, then x this is the term that comes first order, the first order in this matrix, and we simplified this and found that for this process, only this term is going to contribute. Right? This was the only term that was going to contribute. And so we need to calculate this matrix element first, and then we get the matrix element for this process at the tree level. So for that, today we shall do the calculation. For that, first of all, what we shall do is we shall state this is it. This is how it shall be defined, and this is just a normalization. If you do that, now our aim is to calculate what is the volume. This is the volume. So what we need to calculate is basically this phi plus at T1. And you know that phi plus is basically the annihilation number. The annihilation number. So this calculation is quite simple. Just do it. It is a prime equals to we put in a factor of whole cubed. That then give here So this is simple to calculate. We go over. This is now you can replace this by a commutator, right? You can replace it by a commutator for you because the other term will be 0 and value of this commutator is a vectors. So you can perform this a prime integral now and it's that is what we should do. So you know the action of this. So what has happened is that you have got this vacuum on the right hand side. That is what we want to get. Now we have to calculate other things similarly. So what we need to do is the following. So let us now. So is it fine? Sure.
For I T prime dot x.
Yes.
That is K prime 0 at 0 and minus K prime vector.
Just a minute.
Okay.
This one?
Yeah.
Yeah.
So when you write a final answer equal to for I K dot x.
Yes.
That's only K dot x. That is one component.
What should it be?
Should it be K the K0 minus K prime 0 to the still regular?
Where is K prime?
Because delta 3 is only K prime vector minus K 3 vector, right?
Yes.
But you already have K prime 0 term, which is
Yes.
so in writing the similar.
Remember the mode expansion. Go back to the mode expansion. This is an integral of 3k. This, you remember what it is? Remember? You have a zero component. You have a ki component. The zero component is related to the ki component. Right? And so what I mean is that here k0 and k prime are not in and ki are not independent. Although you write it in a 4-vector notation. So let me just explain. This is e to the power of I a 0 prime a 0 plus a I x, right? A prime x. Now you can write this down as according to your signature, since you are using mostly negative, you can write this like this: a vector, a prime vector dot x. And this is you can put anywhere. A0 prime doesn't matter, but this A0 prime is actually related to this K prime vector by the dispersion relation. It's not independent. Although you write it in a compact form. Advantage, why you write in a compact form? This is basically the advantage of covariant notation. Here also, when you integrate, it's true that the thing that you are saying that three vectors are equal. So you can do the three vector. But once you do that, the K0 prime is related to the K0 Ki prime. So therefore, so you don't need a delta 4 for that. It's a 3. So this is done. So now what we need to calculate. So let us do the calculation for the Dirac field now. So suppose I need to calculate this thing. Let's see what it is. Psi plus. And psi plus, you remember that this is the annihilation operator for an electron. So it will annihilate the electron here and it will give you vacuum. So again the standard technique. Let's put E by 2 prime. Right. summation over S, the sum over the spin state, so the electron and positron. Here this is the annihilation operator of the electron, and then we have the S prime, S prime. Then this again we shall write as before. The way in which we wrote down the state detail, we shall write it in the same way. We shall write this as 2 pi over Q by volume V. The electron state, so this will be the diagram S P X. That is what we shall have. And then I can take the summation outside. By the way, this summation will be S prime because this is S. So you have to just change this to S prime. Okay? Because these are dummy. This is the S that you have. Now you have a summation of S prime. Then you have this integral prime. 2 pi whole cube will get cancelled. You will have 2 prime over V. Then I missed another factor. I missed the exponential factor. This will be a constant exponential. Plane wave factor basically E prime dot x. Now I have E prime x. Summation is already outside. Then you have US prime. You can vector. Then you have S prime, E prime, B diagram. S. Once again, you can do this thing, but this time instead of computation, you put the anti-computation, right? So you put the anti-commutator, the other term that you get will be 0, because B will be on the right hand side, then you have to annihilate the vacuum. This part is connected delta, delta is prime, then you have a three-dimensional, 3D delta function. Connected delta allows us to complete the sum over S prime. So if you do that, and Dirac delta you can do the sum over P, the integral over P prime. This will give us once again 2 P volume V. We have P for I for X. It is exactly similar to the calculation that I have done already for the real scalar field. But it is a little bit more complicated because of the presence of the spin term and spin odds. Right? It is exactly similar. Only one difference is that here we had applied for the real scalar field, we had applied the commutation relation. Here we are applying the anti-commutation relation for the Dirac field. So you can now see the full code now. So we have this relation, and we need one more relation. That calculation is exactly similar. I just give it to you as an exercise for you to complete. So, other relation, this is basically the annihilation operator for the electron. And now you need this relation, psi bar plus. Remember that plus is always denoting the annihilation parts, and minus is the creation part. Psi plus is basically electron annihilation. Therefore, psi bar plus will be positron annihilation. So this is acting on the positron state with a momentum P spin S. This is a single particle state, one positron state with momentum P in S. This also you can proceed that way. What you are going to get is the following. P, this will be minus I prime not P dot X, and this is the positron. So positron and positron is P, so this will be V bar. V bar is. So do the calculation. Please check it. So this I this is that's it. So obviously there is a gate. So please do this. Simple to do. Exactly, you proceed in the same way. Define the position state as 2 pi whole cube square root by volume V. And since this is a one particle state, so you know that how do you create this positron? You have to create it by a D dagger. D dagger SP acting on K0 will give you this. Huh? Which one? Yeah, there should be no integral because you see we have performed the integral. And for this I am just writing down directly the result. So please you check this result. Exactly proceed in the way I have shown you and check that you get this. So once you have convinced yourself of these relations, now what you need to do is the following. So I hope you online guys you are with me, right? Is it okay?
Yes, sir.
Yes,
Yes, sir.
professor. Yes.
Good. So now just go back to the other side of the board. So you take this relation and take a complex conjugate of that. So if I just write down the bra version of that equation, so what we will get is just take the bra of the state, so it will become bra electron. And what will happen to psi plus? So if you remember that this psi plus on that side, when it acts on the right hand side, it is basically creating an electron. So if you take a bra of that, get this psi bar minus. What is psi bar minus doing? Psi bar minus is creating an electron. That is annihilating an electron. Psi bar minus is creating an electron on the right hand side. Creating an electron. Go back to the mode expansion. So you have this Dirac field. We are writing this as psi plus psi minus. This annihilates the electron, which is that one. This creates a positron. Take the dual of this. Take the bar of this. So you get psi plus bar plus psi minus bar. Plus is always annihilation. So it annihilates what? It annihilates a positron. This creates the electron on the right hand side. When it acts on the right hand side. So psi bar minus on the right hand side creates an electron. Therefore, on the left hand side, it will annihilate the electron. Right? So what will be this? Psi bar minus this will be. We have to just take the dual of that relation. It will be D, then it will be to the power of I dot x. Instead of QSP, you will get Q bar SP. You could have done already from these relations, but I am just showing you the bra versions also, just to get yourself familiar with these things. So this is done. And this one will equals bar, because this is bar. Go back to this. Write down the mode expansion, take a bar of this. So here you have a US, so bar will be US bar. Here you have a V, bar will be V bar. I am not taking dagger of this, I am considering the bar of this. There is the Dirac adjoint. That is psi bar is psi dagger gamma naught. Remember. So this is how you define Dirac adjoint. Right? I am taking the bar of this, not dagger of that. That is why you will have all bars. My interaction was not psi dagger, it was psi bar. Why psi bar psi? You may ask why not psi dagger psi?
Sir, the
Good.
current.
Good. Psi bar psi is the scalar, the Lorentz scalar, not psi dagger psi. That is why, and you want your interaction to use scalars and the Lorentz transformation. So that is why you have that. Okay. Similarly, what else do you have? You have a psi minus. So psi minus on the right hand side, it creates a positron. So on the left hand side, it annihilate a positron. So psi electron, positron plus E is psi minus x, nothing but 2 3 b psi bar minus this uh, x psi minus means we have a b, right? So this will be the expression. So we have calculated all these things, and now what is left to calculate is the matrix element. That is now simple to do. Let me just focus again. This is not right. So you can see the board now. Is it clear? So I'm just writing this part out. So what we need to calculate now, I have to just rewrite the expression once again. So this one say is a matrix element. So let me say this from the initial state to the final state that I denote it as S1 MIF, and this is basically known as IG equal to X. I'm just using shorthands. I'm not writing arguments. Sorry, what was this? Psi bar minus X means X. And we know what 5 plus on B is. I removed. So this acting on this gave us 1 by 2 gave us A volume B to the power minus that gives you get 0, right? Get 0 here also we have bra 0, so that goes to the wrong. What we have for psi minus acting on this positron thing, this one, given this bra positron thing, was 1 by 2. Let me first write down psi bar minus. For that, we get e power I dot x is what p multiplied by so this is what we should do. All these factors, these 1 by 2 omega by b factors, these you can take it outside the integration over T4x. So basically, I should write this down as nk, right? Nk is this. Nk is b. So these are these factors that I denote as n's, and then these are also some functions of momentum. So I can take it outside the integral to sp sine, right? And then you have this integral over d4x. That is a single integral to work on because it is e to the power of I p prime plus p minus k dot x. So that will give us Dirac delta function. This time, 4-dimensional Dirac delta function. So prime p minus k. That's it. So what we have done is we have calculated that matrix. Is it okay?
Yes, sir.
Good. And remember this decay process diagram. So if I denote this scalar particle by a dotted line like this, and suppose this is the direction of flow of time, in this direction, so going forward in time, and this line, dotted line, denotes the scalar particle, real scalar particle, and this decays. I'm still not given an arrow here, I will give it. Let the solid lines be the fermionic lines. Okay, so that is how I differentiate fermionic particles from the scalar particles. So far, for the 5-foot theory, there was only one kind of particle. So we did not have to worry about whether you took a dotted line or whatever. Everything was solid. Right? Whatever, the vertex, everything. Only one kind of particle. But here you have different particles. One is of fermionic kind, one is of scalar kind, scalar particle, real scalar particle. So that is why I denote the real scalar particle by this and the fermionic particles by solid lines. And this is basically the decay process. So if I say that this is decay and this is my electron, when E is S, this is my positron. Prime. S prime. Okay. I have still not put the direction of arrow in the direction of this positron. But you can understand that this is the vertex. At the vertex, just as if I told you there were 4 lines, here in the vertex, the interaction is psi bar psi phi. So 2 fermionic lines, 1 scalar. So that is why this is the vertex, you can understand the vertex now. And the particle is coming in this direction, so I put the arrow for the real scalar particle. So it is coming at the vertex, getting annihilated. And then 2 particles are getting created. So this is kind of a pair production. Right? Electron and positron is getting produced in pairs, or you can think of it in this way that is it's not really like pair production because there is only one particle involved. It's not. For example, in pair production, what you have is 2 gammas come, 2 gammas they come they scatter, and then it can either scatter to 2 gamma going to 2 gamma, or 2 gamma electron positron. So that is really a pair production. But here we should not think it as pair production. Pairs are getting created, but rather it is like a decay process. That is, the scalar particle is decaying into 2 particles. And obviously, the charges of the 2 particles must be opposite to each other because this is a charge neutral particle. Therefore, these charges must be opposite. And therefore, if one is the electron, the other must be the positron. Okay? So let us now, and another remark that I should make at this point, this is a tree diagram. This is called a tree diagram. So I told you about the anatomy of Feynman diagrams earlier. Every Feynman diagram you can divide into 2 classes. For example, there are trees and there are loops. So you have loops and trees. This is a tree kind of thing. So why tree? Because it is like the branches of a tree. And you know what loops are, we have already seen this loop diagram. So this is one classification of Feynman diagram of trees and loops. This is just, why did you get a tree at this level? Because we just walk through first order in perturbation. That is why you get a tree kind of a Feynman diagram. So this is the Feynman diagram for this process, for this decay process. And now let us come to the electron and positron thing. For the electron, see, both are fermions. So how do you differentiate between an electron and fermion? Then do one thing. So what will you do? What do you suggest to do? Okay, arrow is like this. Then Good. Arrow is like this. See, a very simple solution would be like this. Suppose you want to print in PRD or something, and you can afford to give your color printing chart. Then the simplest thing would be, okay, this is a real scalar dotted line. This is electron. It's a red line. This is positron. It's a green line. And then you give the arrow in this. So you understand whenever it is green, it is positron, and red means electron. But now you cannot give the printing charts. Then what will you do? Then, with your suggestion, as you suggest, reverse the arrow. But then also you have to do, there is one subtlety here. In this case, what you have to do is, see, electron, just look at the right hand side of this line. From here, electron and positrons are getting created. So this is like creation of the particles. Therefore, when electron is getting created, so this is considered as a particle. You put the arrow on that side, the direction of moves. For the positron, you see it is getting created from here. But as Joshi is suggesting that you put the arrow on the reverse side. That is something very obscure, right? But what you can do is, you say that, okay, this is, you put the arrow, so once the arrow is on the reverse side, you know that this is positron, and you say that, okay, that in the direction of the arrow, the momentum is minus. So it means that when it is minus p prime on that side, it is actually p prime on this side. So this is how you draw the diagram. For this, the labeling is this is p, is going in this direction, it's p. Positron is going in this direction, it is minus p prime, but minus p prime in this direction means plus p prime in this direction. And k, there is no problem with the scalar particle. So this is how you fix up the electron and positron thing. And now you can immediately draw the write down the Feynman rule. It's very simple. See here, you only have the vertex. Since you have a vertex, the rule for the vertex is as follows. So what I will do is, so this is the vertex. So I'm not drawing this diagram again here. The rule for the vertex is very simple. You see, as before, we have the coupling constant. The minus I, the coupling constant G, then 2 pi over 4, with 4, 3 times plus 3. So whenever you have a vertex, you have this rule. It's similar to what we had for the FIFO theory, that at each vertex you have the coupling constant. One vertex means one coupling constant, and 2 pi over 4 the overall momentum conservation. So that is the rule for the vertex for this theory. And look at the anatomy of this. How many vertices are there? 1. How many external lines are there?
3.
3, not 2. 3. So this one is also an external line. There are no internal lines. There are no propagators. No internal lines, but there are external lines. So the anatomy, whenever you see a Feynman diagram, always write down the anatomy. How many external lines, how many loops, how many internal lines or propagators, how many vertices. That's it. So external lines is 3, loops 0. Loop 0 means it's a tree diagram. And vertex G is 1. That is the anatomy of this diagram. The rule for the vertex is this. External lines, so we have to be careful here. For an electron, suppose an electron is coming, so this is the direction of flow of time, is coming and falling to this vertex. From the left hand side, it is coming to the right. So it means what? Electron is getting annihilated at the vertex, right? For that, this will correspond to a factor of, suppose, and this electron says has momentum P and spin S. So we will have a factor of NP. What is capital NP? NP is that factor, 1 by square root of 2 EPV. Okay, this is what we will have, and then we will have this spin or thing. So since it is electron coming and annihilating at this point, so this is the rule for the external line. So this is electron annihilation, USP. Again, this is the direction of flow of time. From the vertex, the electron is going in this direction, in the forward direction in time. The arrow is an electron. The fact that this thing is an electron because the arrow is in this direction. So this is electron and the P. Yes. What is the rule for this final rule? In P, U bar is. সেটা আমি টেস্ট করি সেটা আমি জানি না বাট ইউজুয়ালি তো
Ajay, can you hear me?
ওরা শুনতে পাচ্ছে আর সোহম অজয়
Yes, sir, I can hear you, sir.
সোহম এই কালীপ্রসন্ন and অজয় are you sleeping or what?
Yes, sir.
Sir, I am replying, sir. I am Soham.
No, that I can understand, but I think others are sleeping.
Yes, sir. I am here.
No, sir. No.
No, don't think so. Okay, good. So now these are the rules for the external lines for the fermions. Now you see for the positron, it will be something like this. So let me first draw the annihilation thing. So annihilation, what will happen? Positron annihilation. Again, this is the direction of flow of time. On the left hand side of this line, positron annihilation, so this is E plus ES. But this is basically minus P. So that means it is forward P in this. Or alternatively, some people also write it in this way. You can write yes, fine. Then everything is same. And this is basically NP. Once again, this NP, you know what this factor is. Since this is positron annihilation, annihilation means it will be B bar S. Because positron creation comes with factor of B. And positron creation, we've already written down something like this. Positron, this direction is minus this S. Then P bar S. So these are the rules for the external lines. Okay, these are the final rules for the external line. These are rules for the vertex.
That will be just VSP.
Yes.
Last one. Yeah. Last one, just VSP.
Yes. Thank you. Last one is yes. Good. Yes. So these are the final rules for the external lines and the vertex. So you can immediately see the power of this final rule and final diagrams is that whenever you see a diagram, any Feynman diagram at higher order in perturbation theory, you can just directly apply these rules. You don't need to rederive it. Or it's not that if you go to another order, these things will change. Things will remain the same. Only thing is that at higher order, you will get some more rules. At least for this case, you will get another rule because so far there are no loops in this thing. Right? There are no loops. So there you have to go to some higher order in perturbation theory to get the appropriate rule for the loop for the loop in this case. So I
Sir,
have to final rule for the loop. Yes.
sir, for the diagrams, why we are not just reversing the sign of the zeroth component? I mean, we are reversing the sign of the space components. It will be enough to reverse the sign of the time component only.
Which one?
The before on the positron diagram you have written minus p vector. Shouldn't it be just minus p0? I think because it is the time direction.
You can just do minus p.
No, I am asking, is it necessary to change the space directions also? I mean, won't it be enough to just?
Important is the free momentum, right? The energy that is, it is best to write in this way because the free momentum is what is going backwards, right?
Yeah, that is true. Okay, okay.
So you just remember that this is a way of distinguishing the electron from the position. Okay. So now, today we shall not do any more calculation. We shall do calculation tomorrow. We shall do higher order and calculation theory. What we shall do today is the following. And then in the class for today, let us, as I mentioned, that if you want to calculate, so for this diagram, for the vertex, which is this is the vertex. So you can see that we have derived the Feynman rules. Now I can just ask you to just write down the value of this diagram using the Feynman rule without calculating. You can immediately do that, right? Because for vertex, you just put in this factor, for the external lines you put in this factor, you will get this result. Will immediately. I told in the previous class that if you now go to second order in perturbation, and from the first order result, you can now proceed to calculate what is the lifetime of this process. You can calculate the lifetime of this process. But before doing that, we shall not do it now. Before doing that, what we need to find is, are there corrections to this leading order term? If you go to second order in perturbation theory, we have argued in the previous discussion that there will be no correction from the second order term. Why? Because at second order, there are 6 operators. So there will be no correction. So any correction will come at third order in perturbation theory. Third order, there are 9 operators. So you can basically contract 6 of them, so 3 of them will remain. And then there will be corrections. So third order means what? 3 vertices. You have to have 3 vertices. So what kind of a diagram can you have? This particle is coming like this. Can you draw a diagram at third order? There will be 3 vertices. At every vertex, you have 2 fermion lines, 1 dotted line, real scalar field line. So what will happen? What kind of a diagram can you have at third order? There can be many possible diagrams, and you don't know what it is. To know all possible diagrams, what you have to do? You have to apply Wick's theorem, and then you can find all the possible diagrams. But before doing Wick's theorem, can you say what will be a
Sir,
possible diagram? Yes.
sir, I can draw a dotted line.
Yes.
At the end of both dotted lines, there is a electron-positron pair creation and annihilation.
Okay.
And in the scalar line, there is just a loop. It will be 3 vertices. And no, not like that. Yeah, yeah.
So this is another
Then
pattern.
as yeah, then a scalar line,
Then a
dotted line, and then a electron-positron pair. I think it will
You
be.
don't need to put any arrow. So this is, you see, this is a diagram that you will get at third order. Without even calculating, you can now start imagining what kind of diagrams you can get. 3 vertices. So this is the diagram at third order. At every vertex, there will be 2 fermion lines, 1 scalar line. So here also, the second vertex, 2 fermion lines, 1 scalar line. Third vertex. So these are the kind of diagrams that will contribute to this, or that will correct the leading order result. What is this? So you have a new anatomy now. What is the anatomy here? What is the number of vertices? 2. 1, 2, 3. What is the number of loops? 1.
One.
What is the number of external lines? 3. External lines has to be 3. Okay, process. What is the number of internal lines?
3.
Huh?
3, I think.
What is the number of internal lines?
3.
So this is one propagator. This is one propagator. This is one propagator. So these are the number of internal lines. So this anatomy of a Feynman, always look at the anatomy of Feynman diagram. Then you will understand Feynman diagrams very well. But here, from the study of this anatomy, you know the rule for this line. Can you write down a mathematical expression for this? For now, you cannot write down. You can write down vertex, you can write down, vertex, you can write down, vertex, you can write down. This is a scalar field propagator, you can write down, it is I delta f k. There are two kinds of Feynman rules. One is in position space, another in momentum space. Write directly in momentum space. Because position space, what you will get, if you make a Fourier transform, you will get to the momentum space thing. So write directly in the momentum space. Momentum space, this rule you know. External line, electron, we have derived just now, you know. This you know. Fermion propagator we have discussed, you know. So can you write it down? Can you write down the mathematical expression for this? You can write it down. But you can write it. See, this you know, external line. What is the Feynman rule for that? NK. Vertex, you know. This vertex you know. This vertex you know. Fermion propagators you know. This propagator, scalar field propagator you know. External electron, positron, external line we have derived. You can write it down. Actually you can write it down, write everything now, but you don't know one that we shall derive. That we have to derive. See in this, what is the difference between this anatomy and this anatomy? Between these two Feynman diagrams. What is the difference in the structures?
It has a loop.
Here there is a loop. This was a tree diagram. This is a loop diagram. So there is an extra feature of this. It is a loop. Like you see in human anatomy, you have an extra kidney or you have a heart, the lungs. This has extra loop. It's a loop diagram, not a tree diagram. It's the extra feature that you have. And for loop, you don't know what the Feynman rule is. And not only that, I should say that this is a fermion loop. The fermion loop, right? So you don't know the rule for the fermion loop. What we shall derive tomorrow or the day after tomorrow is that for every fermion loop, whenever the loop is totally made up of fermions, you have an extra minus sign. So whatever mathematical expression you write it down. But on the front of it, you have to put a minus sign. That is the Feynman rule for a fermion loop. We shall derive it tomorrow or day after. So this is a diagram. Then there can be other diagrams also. For example, this is a fermion loop, right? Now, suppose at third order, you can get this is the vertex, right? And since this is a third order diagram, we have three vertices. What is the missing thing? It's another diagram that is possible at third order. The scalar particle is coming, decaying, and this vertex again two fermion lines. This vertex again two fermion lines. It is exchanging a real scalar particle. It's an exchange that is going on. It's another. Without calculating, you can just draw these diagrams. This is also a loop. It's a loop. What is anatomy? E is 3, loop is 1, vertex is 3, V is 3. Number of internal lines? 3, 1, 3. Is this a fermion loop? No, it's not a fermion loop. Because all the loop is not made up of fully fermions. It's not a fermion loop. This is the difference between this loop and this loop. It's not a fermion loop, it's a fermion loop. For this, you will have no sign. You can straight away write down the expression for that from the rules that we have already derived. And in tomorrow's class, we shall look at these kind of diagrams, more details. Okay, so let us finish at this point. If you have any questions, you can ask me at this point. Okay, the online guys.
Yes, sir.
You have any
Yes,
question?
Professor.
No question? Okay. So if you don't have any questions, let us stop at this point today. We will continue tomorrow.